Hello and welcome to a presentation on continuous wire rope monitoring systems, retirement for cause and predictive maintenance. In this presentation, we will review definitions, rope deterioration modes, equipment overview, an inspection flowchart, some example inspections, and finally some trending analysis. Introduction to wire ropes. First, some definitions. Wire rope NDE is referred to as non-destructive evaluation or examination. MRT is referred to as magnetic wire rope testing. Wire ropes are safety critical, and failure may result in death or serious injury, loss or severe damage to equipment or property, and environmental harm. Wire ropes are also single points of failure, wherein parts of a system whose failure will stop the entire operation. Ropes are single points of failures that usually cannot be eliminated. Wire ropes deterioration modes. Modern wire ropes deteriorate internally without visible indication. Here are two example types of rope that you may encounter. First is a multi-strand rope, as shown on the left, and an IWRC rope, as shown on the right. If you're not familiar with IWRC, you'll see a definition below. It's an independent wire rope core. The typical deterioration locations for each of the ropes is shown here in red. Some typical wire rope failure mechanisms include interstrand nicking, internal broken wires, as can be seen here, and also corrosion or corrosion pitting. Making rope retirement decisions can be based on some of these deterioration modes. On the left, we'll look at corrosion and wear, and on the right, things like broken wire clusters and corrosion pitting. So under corrosion wear, typically you will use an LMA signal, where LMA stands for loss of metallic cross-sectional area. This is a quantitative signal and can be used as a retirement decision-making signal. On the right, we see the broken wire clusters and corrosion pitting. Traditionally, this is done with an LF signal, which is localized flaw. However, this is more of a qualitative signal and should not be used for retirement decisions. An alternative signal is WRR, referred to as wire rope roughness. This is a quantitative signal and can also be used for retirement decisions. Wire rope's MRT inspection procedure. We have created an MRT inspection flowchart as shown on this slide. Notice that there is some off-site preparation as well as things to do during the on-site inspection, and then again some off-site additional analysis. The first step is really preparation, where you should do some pre-calibration procedures and a variety of function checks and balances. Then, when you are on site, there is equipment to set up as shown here in the picture, including mounting of the sensor head, setting up of the signal acquisition system, and a variety of parameters in a data acquisition box and computer. Then, during the rope inspection, you can push a record button to save the data, do a variety of calibration procedures, including the insertion and removal of a calibration rod into and from the sensor head. This will also be a functional test. Then you can start the rope moving, and after the rope begins to move, you can push our LMA LF reset button and run the rope through the sensor head. You can review the data through our NDT Care version 3.0 software while on site, and a more comprehensive review including report writing for more detailed off-site analysis. Having a detailed MRT inspection flowchart that is followed by your employees with management buy-in is an important feature and should be utilized to get the best possible data. MRT inspection of a winch rope. We'll demonstrate an example based on a locked coil rope, which will show winding on drum damage, corrosion, and corrosion pitting. In this example, we are going to use a 32 millimeter diameter locked coil rope. This particular rope was utilized over a 10-year time frame and was mounted on a mobile winch. Inspection of this rope revealed corrosion in the first and second layer as well as the second and third layers of the rope. Here you see an output chart from our NDT Care version 3.0 software. The top chart is our LMA signal, followed by the LF signal and our WRR signal. Note that the signal trace exactly reflects the rope condition. Small ripples indicate corrosion pitting, interstand nicking, broken wires, both single and in clusters, while large deflections indicate winding on drum damage and second stage corrosion pitting. The x-axis here shows distance of the rope inspected in units of meters. For the WRR, we refer to ISO 4309, the minimum one lay length setting. One lay length is approximately 6.25 times the rope diameter, resulting in about a 200 millimeter scan length. A 2% calibration wire can be seen in both the LMA and the LF signal. This calibration wire was used as a reference so that proper analysis of the remaining parts of rope could be done. Evidence of winding on drum damage can be seen in these locations of the LMA signal, while corrosion-assisted LMA, which is also referred to as second-stage corrosion pitting, can be seen here. Analysis of the same rope, but looking at the WRR at 5 lay lengths, which is the maximum within the ISO 4309 setting, for a scan length of about 1,000 millimeters. Here you can see more clearly in the WRR signal the winding on drum damage, and essentially looks like an inverse of the LMA plot right here. A histogram analysis clearly will highlight possible problem areas based on operator set thresholds. Here, the user selected a -2% LMA between these two thresholds of the light blue markers, so any of the LMA signal less than that 2% is highlighted with easy reference to the location in meters on the rope. You can also see highlights based on threshold settings of the LF and WRR signals accordingly. We'll now look at an MRT inspection of a mine hoist rope. In this inspection, an IWRC rope was utilized. This analysis demonstrated a broken core, corrosion, and corrosion pitting. This analysis was used with an older version of the NDT Care software. We have the LMA signal on the left and the LF signal on the right. Some highlights show some calibration. Here, roughly 3.2%. Again, calibration is a critical first step so that the rest of the data makes sense and help you with retirement decision making. Inspection of the LMA channel shows a dip down to about 11%. This was indicative of a broken core caused by local corrosion. Other aspects of the LMA trace include some slight winding on drum damage as shown here, as well as second stage corrosion pitting as indicated by the LMA going down by almost 13.5% here. Note that corrosion products are not visible in this chart. Then a visual inspection occurred which revealed a broken core which was caused by corrosion due to water ingress and acidic conditions by the mine. Here's a photo of the failed IWRC rope. There were no external damage or signs of broken wires during the visual inspection. The internal core was completely broken due to corrosion. Visual inspection did not indicate issues, while MRT inspection identified this issue through the LMA chart. The rope was cut off at this place and repositioned on the drum without incident. Here's a video showing the cut section of rope and the associated teardown.
Okay, this is our 2-foot section of rope, and the rope has been cleaned, and we can see on examination we do have some outer crown wear to the wires, and some peening is present on the outside of the wires. As we take one strand apart, you will note we have inner strand nicking present on the underside of the wires. Where they meet with the IWRC. So we remove one strand of rope and the second strand. And again, we see exhibited inner strand nicking on the wires in contact with the IWRC. As we further disassemble and remove the strands from the rope. We observe the core of the rope where it has failed. And this portion internal to the rope simply comes out. And this is where localized corrosion has deteriorated the rope to the point where it has actually failed the IWRC. Because of the loss of core support to the rope, upon closer examination, we can see sections of wear where the core had actually failed due to corrosion, very localized corrosion. And due to the pressure increase, how the strands are actually putting pressure on each other due to the failed internal core.
We would now like to introduce our Continuous Wire Rope Monitoring System, or CRMS. We refer to this as our Rope Guardian. The overview of the equipment for this CRMS is going to be demonstrated here using a subsea crane CRMS inspection. Notice there is a storage winch and a traction winch with heave compensation. First, you mount your sensor head with appropriate signal electronics embedded within the assembly, a rotary encoder with feedback signal back to the signal electronics, an interface from the sensor assembly to a computer running the appropriate data acquisition software. Once the load is attached, you can begin your MRT analysis during the deployment of the load. Notice that data is being collected into the system for further analysis and display. Here is a video showing the demonstration of our CRMS system. Note that the rope and CRMS sensor head must be non-contacting to avoid damage to either the rope and/or sensor head. A continuous rope monitoring system, or CRMS, allows the user to predict rope life, optimize the rope operation, extend rope life while maintaining safe operating conditions, schedule rope replacement well in advance, eliminate downtime for unexpected activities such as rope replacement, establish maintenance schedules, and finally, provide alarms, warning, and notifications. We now like to demonstrate a CRMS inspection on an A&R winch rope. This is a spooling operation of a new 78 millimeter diameter, 3.2 kilometer long rope. This is a multi-strand rope with an inspection that lasted roughly 10 hours total. Here is a typical stock photo of a pipelay vessel for the 3.2 kilometer or roughly 2 mile A&R winch rope spooling operation. Again, using our NDT Care version 3.0 software, the same three signals, LMA, LF, WRR, we can see the inspection here. Notice the x-axis is in meters. We're over 3,000, so roughly 3.2 kilometers is the total inspection. There are a few inspection artifacts which are likely due to some stick-slip movement of the winch. We'll see that more clearly in an upcoming slide. Notice that the LMA is well below 0.5%. Please consider that wire ropes are complex machines with a great many moving parts. Therefore, ropes must be well lubricated to allow free movement of individual wires, causing small variations of wire positions in the rope during the spooling operation. These minute changes of the rope structure are reflected in the LMA and WRR traces as so-called rope noise. The chart clearly shows these minuscule changes of the rope structure and the associated rope noise as the spooling conditions change. With our software, we can zoom in for easy analysis. Whereas before you saw the full 3.2 kilometers, here we're showing roughly a 100-meter segment, so from roughly 700 meters to about 800 meters. You do this by clicking on the various tabs up here, and you can zoom through and see all the various sections of the rope. You can also do an analysis as a function of time, which shows all the variety of starts and stops during this 10-hour inspection. So now the x-axis is no longer in distance, but in time measured in seconds. You can see, as part of the LMA, points where it is a flat line, this is the time when the rope has stopped. It's more clearly indicated with this new chart down at the bottom, which is no longer WRR, but it shows the rope payout in blue. So this is the rope going out, and it goes all the way up to the 3.2 kilometers. The red signal trace with the scaling on the right is the rope speed. Notice the axis scaling here is meters per second. As a reference, this spot right here represents roughly 4 inches per second. If we were to zoom on these sections of the spike, you will see small anomalies here in the rope speed right here, which again, from our indications, indicates a possible stick-slip operation. A preventative maintenance and trending tool will allow for early detection of corrosion and an immediate corrective action, for example, some improved lubrication. Also, some early detection of accelerating wear and interstrand nicking, which can indicate a need to reline sheaves to stop further degradation. And finally, an ability to monitor the development of local damage at rope crossover points on a winch drum, thus allowing for the optimum time for rope repositioning on the drum. A CRMS rope guardian system can help you with all of these. The following CRMS inspection demonstration trials. This is a discarded 75 millimeter diameter multi-strand rope with some artificial flaws. Corrosion is observed during multiple runs in a forward and reverse direction. Here's a quick video showing this operation. Notice the sensor head here, the gray in the middle with the rope going through it. The reason for the forklifts on the assembly with this prototype is we want the rope to go through the sensor head without touching. The actual installation of the box was much easier than the assembly that is seen here. This rigging setup could be considered a simulation of an A&R winch. This particular rope was analyzed using 9 different tests. We took this data to demonstrate a new add-on tool for our NDT Care software, which is our 3D version or trending analysis. So here all 9 runs are shown, first for the LMA signal, and we're showing you a front-on or 2-dimensional view. You can also see this as a 3-dimensional view of the same inspection. Like most CAD programs, once you have this tool, you can click and rotate this any way you want, but we do have 2 default settings which are shown here, the 2-dimensional and 3-dimensional views. But we do allow the user to click on the actual figure and rotate it in a 3-dimensional space. We have this for LMA, LF, and WRR, but for this presentation, we're only going to show the LMA and WRR. Here's the 2-dimensional view of the WRR of the 9 signals, and here's the 3-dimensional view. This will allow for multiple inspections as part of your preventative maintenance program. If you have any questions on this presentation, please don't hesitate to reach out using the contact information shown on the left part of your screen. Thank you.